Hi, welcome to the second of the GCSE physics lessons on the topic of energy, where I've looked at some energy stores and energy transfers in last lesson. Today, we're going to be doing some calculations based on two of those different types of energy. So make sure you've got a pen, a pencil, and calculator ready for this topic. There's also a worksheet linked to this lesson. You can complete that worksheet online and submit it when you're finished, or you can print that worksheet, complete it, and send a photo. I'm going to share my screen now. We'll get ready for the title of the lesson, and we'll begin. Right, so our title is JPE and KE. You've probably figured out that that stands for gravitational potential energy and kinetic energy. So I'll be calling them GPE and KE in this lesson: gravitational potential energy and kinetic energy. Okay, so let's look at gravitational potential energy. We said that gravitational potential energy was energy stored in an object when it was lifted up, but gravity wants to pull it back down again. Now, why do some objects gain more or less gravitational potential energy than others? For example, this red box and this blue box, when they're lifted up on top of the shelf, gain different amounts of energy. Now, why would that be? Well, the first thing you might notice is that the higher up we lift something, the more gravitational potential energy it gains. And you might notice that the blue box is larger than the red box, and it gains more energy even when you lift it to the same height. That's because the weight of the object makes a difference. Now, for the weight of the object, we're talking about its mass, so how many kilograms of it there is, and how strong gravity is. Although we'll almost always be thinking about gravitational potential energy here on Earth, where gravity, the strength of it, isn't going to change, we can do this some anywhere. And scientists might have to do this on different planets or for spacecraft in orbit, all sorts of things. But what it means is that the amount of gravitational potential energy an object gains depends on its mass, depends on how strong gravity is, and depends on how high you lift it. And that gives us a calculation which looks like this. We say that the gravitational potential energy, so E, we'll put a little T down here to remind us that it's potential energy, equals the mass of the object in kilograms multiplied by the strength of gravity, the gravitational field strength, multiplied by the change in height, how much higher you lift it. So we'd say E equals mgh. Potential energy equals the mass of the object times gravity times the height change. So E equals mgh. Now, this is a formula you need to remember. And just like in every formula we need to remember in physics, we will teach you a mnemonic so you can remember those quantities in the right order. E equals mgh. We say EMGH, eating my green Haribo. Like every triangle we teach you, the first letter goes on top of the triangle, if you write it as a triangle, and every letter after that goes on the bottom row of the triangle. So it ends up as a formula triangle looking a bit like this. So energy, mass, gravity, height. Now, if we're going to rearrange that, it looks like it's harder to rearrange. It's not. If I want to work out energy, I cover up the E in my formula, and I'm left with energy equals mass times gravity times height. It's an easy one. But of course, I might get other rearrangements in the calculation. I might be asked to work out the mass of an object. I cover up the mass, and that leaves me with energy divided by gravity times height. So I would do the energy it gains divided by the strength of gravity times the height. So you can see how you rearrange a triangle like that, even though it's got 4 letters in it. If I want to work out the height something has been lifted up, I cover up the H. Height equals the energy divided by the mass times the strength of gravity. So these rearrangements work even with these big 4-letter triangles, nothing to be worried about. So any of those rearrangements can be done with that. So you'll be given some calculations to do using that gravitational potential energy formula. For example, here's an example. Calculate the GPE gained when a boy with a mass of 50 kilograms is given a fireman's lift at a height of 2 meters. The strength of gravity on Earth is 10 newtons per kilogram. It's worth looking at that number, that 10 newtons per kilogram. Whenever we're doing these GPE sums here on Earth, if you're not told the strength of gravity on Earth, you can use the number 10. The strength of gravity on Earth is 10 newtons per kilogram. So, straightforward enough calculation. If I look at my formula triangle, if I cover up energy, then I'm left with mass times gravity times height. So I've got mass of 50 times strength of gravity 10 times the height that we're lifted up 2. So 50 times 10 times 2 gives me 1,000. And of course, I need to get the units to get my final mark in physics. So it's 1,000 joules is a unit for energy. So again, the classic way, you write out your calculations in physics, write out the calculation you're doing, write out the sum with the correct numbers in it, and then give the answer with the correct unit. Let's look at a rearranged one. So after dropping the Curiosity lander, so this is one of the spacecraft that NASA landed on Mars. So after dropping the Curiosity lander, the Sky Crane, that's this machine here, rose into the atmosphere of Mars. If the Sky Crane gained 333,000 joules of GPE, and it has a mass of 900 kilograms, how much height did Sky Crane gain? The strength of gravity on Mars is 3.7 newtons per kilogram. Okay, let's get my sketch pad here. So I'm trying to work out a height here. So if I look at my triangle, height is the energy divided by the mass times gravity. So if I'm writing out my sum, it's the energy, 333,000, divided by the mass, 900 kilograms, times the strength of gravity on Mars. So that's what my sum looks like. So once you've written that sum out, you can really just bash those numbers into your calculator there. I'll use my calculator on my phone, get the answer there. Let's have a look. 900 times 3.7, 900 times 3.7, it gives me 3,330. So I've got 333,000 divided by 3,330, which gives me an answer. I'll just do the sum on my calculator. 333,000 divided by 3,330 gives me 100. And it's a height, so it's 100 meters. So there you go. So rearranging that GPE triangle, like all triangles, cover up the thing you're trying to calculate and see what sum you're left with. So there are GPE sums on the worksheet for you to calculate. There's also kinetic energy calculations. So we say that kinetic energy was the energy stored in moving objects. So why might some things have more kinetic energy than others? Well, if it's moving, the two things that are going to make a difference are its mass, how many kilograms of it there is. So an object with more kilograms has more kinetic energy when it's moving, and how fast it's moving. The faster it's going, the more kinetic energy it has. So what does the calculation for that look like? Well, the calculation for kinetic energy is that the energy, E, and I've got a little K beside it here to remind myself that it's kinetic energy, equals 1/2 times the mass of the object in kilograms times its velocity or speed squared. I need to square a velocity or speed before I do this kinetic energy calculation. It's another learning formula. E equals 1/2 mv squared. So what's our mnemonic for that one? Well, you were eating my green Haribo. Why do you not eat my green Haribo? Because that's the same as eating half my vitamin squares. I need my little vitamin squares to stay healthy, my little sweets. So eating my green Haribo is the same as eating half my vitamin square. So E 1/2 mv squared. So you can see how we've got the squared in there to help you remember that. Again, the rearrangements, although it looks like the rearrangements are a bit of a pain, they're not. If you write it like a triangle, E, goes on the top line, half mv squared is your rearrangement. If I'm trying to work out the energy, cover that up, no problem. Energy is a half times the mass times the speed squared, no problem. But you could be asked to work out either of the two on the bottom. So let's look. I'm trying to work out the mass of an object covered up. The mass of an object is the same as the energy divided by a half times the velocity squared. So that's my mass rearrangement. What if I was working out the velocity? Well, let's have a look. I cover up v squared. V squared. That equals energy divided by a half times the mass. Now, you might spot it here that if I'm trying to work out the speed, I've just given myself a calculation to work out the speed squared. So if I'm going to work out the speed, I need to take a square root of that answer. So I need to do the square root of energy divided by a half times the mass. So you may have to do a square root rearrangement to find that answer. So those are all our rearrangements of the kinetic energy calculation. So for example, here's a standard one to work out the kinetic energy of an object, looking at the Sky Crane spaceship on Mars again. When the Sky Crane flew upwards, it had a velocity of 28 meters a second. The mass of the Sky Crane was 900 kilograms. How much kinetic energy did it have? Well, our kinetic energy, E, equals a half times the mass times the speed squared. So a half times the mass, which is 900 kilograms, times the speed squared. So I'm going to have to do 28 squared. So a half times 900 times 28 squared. Pop that into your calculator. I'll get 352,800. And it has to be joules because it's an energy store. So you're just putting those numbers into your calculator, getting the right answer. A rearrangement could be an example like this. Mo Farah's got a mass of 60 kilograms. If he's got 1,470 joules of kinetic energy, at what velocity is he running? Okay, let's have a look. So I need to do my rearrangement, v squared. So v squared is the energy divided by a half times the mass. Now I'm going to have to do a square root at the end of this, but let's do my energy, 1,470, divided by a half times the mass, which is 60. So I've got 1,470 divided by a half times 60. So 1,470 divided by 30, if I grab my calculator, 1470 divided by 30 gives me 49. But don't forget, to find v, I said I'd have to get the square root of the answer. So v squared equals 49. So v is the square root of 49. And that's 7. It's a velocity, so it's in meters per second. So if you're working out a velocity, don't forget when you rearrange the equation, you're rearranging it for v squared. So you're going to have to take a square root to find v, or to find the speed that an object's moving at. So those are your calculations for the kinetic energy rearrangement. So you're going to have calculations on the GPE formula. You're going to have calculations on the kinetic energy formula. But we're also going to do questions where those two sums are linked together. Now, how could those two sums be linked together? Well, we have to remember that when an object is falling, what's happening is its GPE store is being transferred to its KE store. It starts off with energy stored in it as GPE, but as it falls down and gets faster and faster, that GPE store decreases and that kinetic energy store increases. So if we know the amount of GPE an object has at the top of its fall, we know how much kinetic energy it will have at the bottom of its fall. One way I like to think about that is it was a skateboarder going up and down a ramp. Got a slightly unrealistic simulation here, but I'm going to turn on a bar chart at the side here. Now the bar chart at the side has two bars, a blue bar, which represents the GPE, and a green bar, which represents the KE. Now, if we have a look at the very top of the slide, we can see that all the energy is stored as potential energy. So I could do my E equals mgh sum and work out how much potential energy, GPE, the skater has. As the skater moves down the ramp, you can see that the amount of potential energy decreases as they get lower and lower down. But the amount of kinetic energy is starting to increase as they get faster and faster. By the time they get to the bottom of the ramp, when they're going their fastest, they have zero potential energy, and all of the energy is now stored in them as kinetic energy. As they go back up the other side of the ramp and start slowing down, their kinetic energy store starts decreasing, but their potential energy store starts increasing as they get higher up the ramp. So as we run the animation, you can see that going up and down a ramp or falling downwards is transferring your GPE store to your kinetic energy store. It's worth looking at that yellow bar at the side as well, which just adds the two of them together. You can see that the total amount of energy stays the same. We're just transferring energy from one store to another. But if I counted the total amount of energy, it would stay the same. That's going to help us with these calculations. So a calculation might start like this. Right, we've got an Olympic diver, mass 50 kilograms, climbs to the top of the diving board. If the strength of gravity is 10 newtons per kilogram, how much GPE do they gain? Well, we've just got a standard GPE calculation here. The GPE equals mass times gravity times height. So we've got mass of 50 times gravity of 10 times height of 10. 50 times 10 times 10 gives me 5,000 joules of GPE gained. So this is like our skateboarder at the top of the ramp. Our diver is at the top of a diving board with 5,000 joules of gravitational potential energy. But then the next part of the question says when the diver jumps off the board, they fall, their GPE is transferred to kinetic energy. What velocity does the diver have as they hit the water if all of their GPE is transferred into KE? Now look, there are no numbers in this question. You're thinking, how on earth can I work out the velocity? If I'm trying to work out the velocity using my kinetic energy sum, how am I going to do that? Well, the important thing to remember is the amount of potential energy they start with is equal to the amount of kinetic energy they end up with. So if they start with 5,000 joules of potential energy, they're going to end up with 5,000 joules of kinetic energy. So I can start my kinetic energy sum by saying, hey, I know how much kinetic energy they have, 5,000. 5,000 is a half times 50, his mass, which hasn't changed since the first question, times his speed squared. I've just done my rearrangement, really, for working out velocity. So v squared is 5,000 divided by a half times 50. So v squared is 200. So I need to do my square root. Root 200 gives my velocity of 14.14. All I did was worked out the GPE in the first sum, but I know that that was the total amount of kinetic energy I had at the bottom. So I took the answer from my GPE sum and I used it as the energy number in my kinetic energy sum. That lets me find the velocity. Now, one of the things they will very often say in one of these GPE and KE sums is that if we work out a speed, we say, fair enough, the diver is going to hit the bottom at a speed of 14.1. In real life, they actually end up a bit slower than that. In real life, the velocity was measured at 13.5 meters per second. So why was it less than the number we got? Well, to do that, it's probably worth looking at my simulation again. this simulation isn't realistic because it's missing one really important force, which we see a lot of in real life, and that force is friction. If I set the ramp up with friction, you can see, oh, we've now got another form of energy, thermal energy. As the skater goes down the ramp, some of that gravitational potential energy becomes thermal energy because of friction. So not all of the GPE in real life will get transformed into KE. With the diver, it'll be because of air resistance. So not all of the GPE ends up becoming kinetic energy. So that's how we do those transfers. And there is a question about calculating the speed of an object once it's fallen down at the end of your worksheet. So we've got those worksheet questions to do on GPE, KE, and transfers. Once those are done and dusted, you can then use the answer sheet in there to mark your questions. And once those are marked, you can submit your worksheet. I'll stop sharing my screen now. So please complete the worksheet questions, show your working out for each of the calculations, and then mark them using the answer sheet. Do any corrections in a different color ink, and then submit your marked and corrected worksheet at the end of the lesson. Thanks, and I'll see you next time.